Organization for Health, Research Organization for Nanotechnology and Material, Research Organization for Agriculture and Food, Research Organization for Governance, Economy and Community Welfare. BRIN catalyzing research and innovation to develop an advanced scientific ecosystem in Indonesia with two main targets. BRIN realizes the tremendous potential of the nation's youth in the field of science and technology. Thus, various research and innovation policies are being formulated to develop and cultivate human resources with high competence and aptitude in science and technology. Creating many excellent programs is a form of BRIN's commitment to researchers, innovators, and the general population from various disciplines across the nation. The research and innovation ecosystem quality improvement in Indonesia is also realized through the collaboration of various ministries, institutions, domestic industries, and regional governments, to name a few, by forming the Regional Research and Innovation Agency, or RIDA. Moreover, cooperation with various foreign research institutions continue to be developed through active participation as member of various organizations and international forums. BRIN organizes research into a more effective and efficient process by integrating human resources, infrastructure, and budget from various research and development institutions. Oriented by a national research priority, BRIN routinely enacts comprehensive evaluations from various research and development institutions. This effort is supported through the continued management and improvement of various research and innovation facilities located across 17 regions of Indonesia, dedicated towards the development of science and technology. BRIN continues to improve our contribution to research and innovation towards national development by developing and revitalizing 4 areas of science and technology, or KST. An integrated area consisting of research laboratory facilities, testing laboratories, and industrial facilities for both startups and SMEs.
Can I be heard?
Oh, clear.
Good day, everyone. Assalamualaikum. May we all be blessed with good health. Acting as today's host, my name is Damar. I am one of the BRIN Communication and Publication Officers. First and foremost, we would like to send our regards to our distinguished guests, Representative Chair of Research Organization of Nuclear Technology of BRIN, Mr. Maman Kartaman, Section Head of Radiochemistry and Radiation Technology of the International Atomic Energy Agency, IAEA, Ms. Selina Horak. Our speakers, BRIN researcher, Mr. Kristejo Kurnianto, and Industrial Technologies of IAEA, Ms. Hana Asma Afum. Our moderator, BRIN researcher, Mr. Rozik Himawan, and all participants. Thank you for coming to International Atomic Energy Agency, IAEA, Collaborating Centers webinar series on advancing industrial radiation technology. On the topic, development and implementation of low-cost X-ray CT system and its applications. Before we proceed, we would like to invite the section head of radiochemistry and radiation technology of the International Atomic Energy Agency, IAEA, to deliver her remarks. Please welcome Ms. Selina Horak.
Thank you very much. Good morning, afternoon, evening, and thank you so much for organizing this webinar. Thank you for showing all the attendees to this webinar on advancing industrial radiation technology with the main topics: development and implementation of X-ray CT system and their application. It is a real pleasure to potentially gather expert, practitioner, regulator, and partners to talk about technology that's changing how we inspect, design, and secure the world around us. Industrial X-ray CT is no longer a niche tool. From ensuring the integrity of critical infrastructure to validating complex additivity manufacturing parts, CT gives us the ability to see inside material and assembling with precision what once was impossible. That capability brings huge benefits: better quality, fewer failures, faster innovation, but also clear responsibility. Reliable measurements, effective radiation protection, strong standards, and skilled people. That's where the International Atomic Energy Agency could make a difference together with our partners. Through guidance material, upcoming e-learning material, technical cooperation program, coordinated research activity, and targeted training, the IAEA helps countries adopt CT technology in ways that are safe, practical, and internationally harmonized. And a vital piece of this ecosystem that IAEA is working is the collaborating centers. And this is our case here. No? Our speaker is one of the IAEA collaborating centers who are contributing to our programmatic activity. These centers are practical hubs. They train technicians, regulators, provide reference measurements, and test artifacts, run pilot projects that de-risk new methods, and act as regional bridge to expertise reaches every member state. They turn global guidance into local capability. Today, we'll hear about recent technical advances, real-world application, and, well, what IAEA is also doing in collaboration to this activity. I encourage all of you to think about concrete partnership and next step. What support does your country or organization need to move forward safely and confidentially? Thank you again, and I'm very looking forward hearing from all the experts here in this webinar, and I will handle to the moderator again. Thank you very much and welcome.
Thank you very much, Ms. Selina. Next, we would like to invite the representative chair of BRIN Research Organization of Nuclear Technology to deliver the opening remark. Please welcome Mr. Maman Kartaman.
Okay, thank you, Ms. Damar. Distinguished guests, esteemed colleagues, ladies and gentlemen, good evening to all participants from BRIN from Indonesia, and good afternoon for other countries participant. On behalf of Research Organization for Nuclear Technology, we would like to welcome to our webinar, IAEA Collaborating Center webinar series. I think it is the first time webinar in 2026. I think thank you to everyone for coming and joining us to the webinar. I would like to extend a warm welcome to our distinguished colleagues from IAEA, Ms. Selina Horak and Ms. Hannah Afum. Thank you very much for joining us today. And this webinar, there are two speakers for today's webinar. First speaker is Mr. Kristejo Kurnianto from Research Center for Nuclear Beam Analysis Technology, and Ms. Hannah Afum from IAEA. Mr. Kristejo will present about the development and implementation of a low-cost X-ray CT system and its application, while Ms. Hannah will present about the enhancing disaster management with AI augmented NDT for engineering assessment. My sincere appreciation also goes to our speaker for sharing their expertise. I think both of all speaker has a strong experience about about this topic. And to all participants, researcher, industrial professional, and student for taking the time to be part of the webinar. Today, we will discuss about NDT, non-destructive testing, one of the key technologies that support safety, reliability, and efficiency in many industrial sectors. We know that NDT play an important role in ensuring the integrity of the facilities while protecting people and environment. Indonesia Development NDT has strong supported by long-standing cooperation with the IAEA through various national, regional, and research programs. This collaboration has contributed significantly to capacity building and also technology transfer. As we know that in 2015, Indonesia has designed it as an IAA collaborating center in NDT, and we are currently preparing to extend this cooperation for a third term. This reflects our continued commitment to this partnership. I think today's webinar, jointly organized by the collaborating center from Malaysia, Morocco, and Indonesia, and also Indonesia, reflect the strong spirit of international cooperation and knowledge sharing. Finally, I hope this session will be informative, engaging, and beneficial for all participants. With that, I'm pleased to officially open this webinar. Thank you very much, and I wish you a productive session. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Mr. Maman. Dear all participants, may I ask you to turn on your camera? We would like to take some screenshots. Begin with my countdown. 3, 2, 1. 3, 2, 1. Plus 3, 2, 1. Thank you very much. We have about a 90-minute session for presentation and discussion. So without further ado, we would like to invite our moderator, Mr. Rozik Himau. Mr. Rozik is one of BRIN senior researcher of the Research Center for Radiation Processing Technology. His research field focus on material testing and evaluation, mainly using non-destructive testing, X-ray radiography, and ultrasonic method. Mr. Rozik, the screen is yours.
Thank you, Ms. Damar, for the kind introduction and for the leading the opening session. Now I will continue as the moderator for today's scientific presentation. Good evening, good afternoon, and good morning, distinguished speakers, guests, and participants. Welcome to the IAEA Collaborating Center's webinar series. First of all, I would like to acknowledge Selina Horat, Section Head of Radiochemical and Radiation Technology IAEA, Bapak Maman Kartaman, Representative for Head of the Research Organization for Nuclear Energy BRIN, and Hannah, the Industrial Technologies IAEA, and of course, our keynote speaker today, Pak Chris Tejo. Yeah. Pak Chris, thank you all for being with us today. In this section, we would like to provide two main agenda. The first is the scientific presentation, and the second one is the official introduction and launching of the new IAEA Coordinated Research Project. The first speaker, ladies and gentlemen, our first speaker is Mr. Chris, or Pak Chris, a researcher from Research Center for Nuclear Beam Analysis Technology, BRIN. And in this moment, I would like first to share with his curriculum vitae. Pak Chris graduated as a Bachelor of Engineering from Gajah Mada University on Nuclear Engineering and from Master Engineering from the University of Queensland, Australia in Computer Science. For the work experience, he started working at primary Patan, start from 2002 as instrumentation staff, and now he became a senior engineer, but he also experienced on management position as well. And for the activity, he mainly involved on engineering, such from and focusing on the radiation imaging technology. And for the international contribution, he was involved for many activity relating to the IAEA, such as from the technical meeting and RCA training course, regional workshop, technical working group, and etc. So for the various expertise, various experiences, Pak Chris and his team has successfully developed a low-cost city system, and he will share today what is his experience to develop the system, city system. So I will not be longer, but please be remind that this presentation will approximately 30 to 40 minutes. And if you have a question, please type on the chat column, and chat column, and then after that we will read one by one, and Pak Chris will answer. And for the question and answer, I will provide this session after the second presenter provide the presentation. So now let's start for the first presentation. Pak Chris, please begin your presentation. The screen is yours.
Okay, thank you, Pak Rosik. Let me share my second screen. I hope you can see it. In 1 second. Okay, can you see my presentation?
Perfect, Pak Chris.
Okay, thank you so much. Okay, so good morning, good day, and also good afternoon, distinguished colleagues, ladies and gentlemen. Thank you to the IAEA for the opportunity to present our works. My name is Chris. I'm from Nuclear Energy Research Organization, BRIN, Indonesia. Today, I will present our experience in the development and implementation of a low-cost X-ray CT system, including its detector development, industrial application, and future direction, such as dual energy CT. This presentation starts with the motivation and basic principle of X-ray imaging, and then I will discuss on the development of X-ray imaging detector, particularly a low-cost fluoroscopic detector inspired by the IAEA guidance. After that, I will present industrial application and its development of a complete low-cost CT system before concluding with the future research direction. Let me first explain the background and motivation for these works. X-ray radiography and computed tomography are essential tools in many sectors, ranging from medical, diagnostic, to industrial quality control and research. Despite their importance, access to this technology remains limited in many parts of the world due to the high system cost, complex maintenance, and dependence on property components. These challenges are particularly significant in developing countries. So to better understand this challenge, it is helpful to look at the global context. This map shows the global distribution on the Human Development Index. We can clearly see that the access to advanced imaging technology closely follows economic and technological development. One key objective of our work is to help reduce this gap by developing affordable, reliable, and locally maintainable X-ray imaging system. Based on this context, I will now explain our specific motivation and alignment with the IAA programs. X-ray imaging is based on the interaction of X-ray with matter through absorption and scattering. As X-rays pass through an object, different material attenuate the beam to different degrees, creating image contrast. In conventional radiography, a single projection produces a two-dimensional shadow image. However, in computed tomography, multiple projections are acquired from different angles and reconstructed computationally to produce cross-sectional and three-dimensional images. One important imaging modality that bridges radiography and CT is fluoroscopy. As you can see on the screen, fluoroscopy is one of the earliest X-ray imaging techniques, producing a visible image on a fluorescent screen. Transmitted X-ray excite the screen and then emits visible light that can be observed or recorded. So the key advantage of fluoroscopy is real-time imaging, which has driven major technological development, including image intensifier and digital fluoroscopic system. You can see on the picture that historically, one of the earliest fluoroscope was developed by Thomas Edison in 1896. So it's, I think, just 1 year after X-ray discovered by Röntgen. Yeah. So at the beginning, in the euphoria of X-ray, you can see they don't know about the dangers of the dose, so they use everything using X-ray, even just for checking the shoes. Yeah. However, this technology is actually is an old technology, but over time, fluoroscopy evolved alongside other X-ray imaging technologies. So X-ray imaging technologies have progressed from screen film radiography, computed radiography using imaging plate, yeah, like this one, and then indirect digital radiography. So X-ray converted to the visible ray, and then grabbed by the electronics or camera, and finally using the DDR or direct digital radiography. While modern flat panel detectors offer excellent performance, they are also expensive and difficult to maintain locally. This creates an opportunity for an alternative detectors architectures. So this brings us to an important contribution from the IAA, that the low-cost digital radiography concept. So the IAA Radiation Technology Report number 2 provides a very practical and influential reference for low-cost digital industrial radiography. The key idea is replace expensive direct conversion detectors with an optically coupled system consisting of scintillator screen, a mirror system, and a low-light digital camera. This approach significantly reduces cost while maintaining sufficient image quality for many industrial applications. So the modular architecture also improves maintainability and flexibility. Based on this IAA concept, Badan and later BRIN developed a low-cost digital fluoroscopic detectors. The fluoroscopy box was redesigned to the field of the view and replaced with the new camera technology with a more quantum efficiency and also increased resolution. And this change made the system more suitable for industrial environments and larger objects. So to support this design decision, we performed detailed evaluation and simulation. So you can see this is first and second generation of our detector. The detector was evaluated using ARTIST and GN4 simulation software. So through the iterative development, the system evolved from a small field of view prototype to become lightweight detector with a bigger, like 40 by 40 centimeters field of view and a 20 megapixel camera. So this step-by-step improvement approach proved very effective. With a stable detector, we move on the real industrial testing. Yeah, one of the first industrial application was real-time inspection of an alloy car wheel casting. So common defects such as porosity, shrinkage cavities, and cracks can be clearly observed using fluoroscopic imaging. This application demonstrates that low-cost system can deliver real industrial value. Actually, we put our detector in very harsh environment in car wheel fabrication. So, and they use for, I think, more than 6 months, 24 hours, and this detector is works perfectly. So from the real-time fluoroscopy, yeah, you can see we put it's still hot, yeah, from the casting, and put on the manipulator, and then close the door and start inspecting, and we can check the porosity, shrinkage defect or cracks, yeah, on all of the part of the wheel. It's like on the hub, spoke, overflow, and all the part of the rim, yeah. Next, we will talk about the computed tomography. So by combining an X-ray source, a rotating object states, and a digital detector fluoroscopy can be extended to CT. So CT enables three-dimensional inspection and provides much more detailed internal information than just 2D radiography. So we begin with the simple CT configuration to validate the concept. So I think this is in early 2015, an initial CT system was developed using a portable X-ray source, medical digital detector array, and parallel beam geometry, and reconstruction was performed using an in-house software developed in LabVIEW, and this system served as a test platform for further development. We then integrate the fluoroscopic detector into CT imaging. So in 2016, we conducted IAA RAS expert meeting on computed tomography and digital radiography. And at that time, Professor Uwe Wirth from BAM Germany, as an IAA expert, guide us to improve the first beginning of CT fluoroscopic detector. So we can, sorry, I have to improve the, I'm sorry, it's technical problem. I cannot play my video. Okay, just skip. So at that time, we start to arrange and using a fluoroscopic detector for CT. Yeah. So the low-cost fluoroscopic detector was successfully adapted for CT inspection of the casting product. And this demonstrated that optical detector actually can be effectively used for CT, not only for fluoroscopy. So building on the success, we developed a complete low-cost industrial CT system. So you can see we develop whole system, yeah. So with the rotating table, yeah, that rotate the object, and also we put all the system on a very stable base using granite base, and also we have a lifting column for position adjustment. And at this prototype, we use X-ray source, continuous X-ray source, from 0 to 100, sorry, actually it's from 80 to 180 kilowatt, 500 watt, and with a maximum 3.12 milliampere, and the focal spot is just 0.4 millimeter. Yeah. So at this time, we tried at the to build a whole complete city system with a safe compartment. So the city housing consists of stainless steel and lead shielding to ensure radiation safety. And also we use a water-cooled X-ray generator and an A4 sized fluorescent screen enable imaging of relatively large objects. Additionally, lead shielding was also added to protect the high-resolution camera from radiation-induced noise. So we also develop our software, in-house software, to control, and acquisition software was successfully developed in our institution. So one important aspect of this system is the cost. You can see the total after-tax cost is around 430 million rupiah. It's like around 30,000 US dollar. Later I can compare with the commercial one. Yeah. And this is including the components and also the labor cost. And I think the most expensive component, I think the X-ray, yeah, I think it's almost 25,000 US dollars. So actually we built from scratch all things. Yeah. Okay. So the total cost of the complete city system was approximately 30,000 US dollar. This is order of magnitude much lower than the commercial industrial city system, which can cost hundreds of thousands to millions of dollars. For example, BRIN also have two commercial city system, Skyscan 2214. Actually, I know the performance is a bit lower than the commercial one, but actually this is much enough for city. So you can see this is like almost 1 million US dollar, and we can build just 30,000 US dollar. Yeah. And also the performance we can compare is still comparable. Yeah. And probably, yeah, the resolution and also the acquisition time is longer, but it's okay. Yeah. We also support with the software for CT, for acquisition software, reconstruction software, analysis software, and also simulation software. So this is outside of this cost. Yeah. And currently we just bought a new CT system for the big one, yeah, with workpiece weight on up to 250 kilogram, with a very big space, and actually we use this for big object and also for archaeological like big fossils and we need higher X-ray. Yeah. So radiation leakage and system performance were tested and certified by our local center for safety, and both non-imaging and imaging tests were conducted, including spatial resolution evaluation and also CT imaging of welded pipes. Yeah, so you can see the dose it's low enough, and or usually we operate this like 2 meters from and this is still enough, and the system was certified as a safe for operation. Yeah, so we can close the door. There is a lead glass. Yeah, so we still can see the object directly, and also during all the scanning system we can operate this CT system safely. And I will now show several application examples of this CT system. Yeah. So you can see this is a CT on casting product. Yeah. This is a, I think, motorcycle engine. Yeah. And we also try to scan turbine blade. Yeah. Yeah, and also some pipe joint. So based on this, we can internal defect visualization in metal casting, and we also improve defect characterization compared to the 2D radiography. So it's quite interesting. Even with low cost, we can got the very interesting internal of combustion engine with a non-destructive method. So actually we rotate the object and then reconstruct and then analyze using a visualization software. So it's also important because some of our researchers also interesting to try to help their research. So the CT system has been applied to phytosanitary inspection. So this application include non-destructive inspection of agricultural product. As you can see, we use salak, it's a snake fruit, yeah, it's like this one, and we scan it, and we very clear see all the internal of this fruit. And actually Indonesia is very it's a where produce a lot of fruit because we are a tropical country. So using this, we can help the researchers to recognize in the if there is a pest inside, or even when they find a new variety of fruit. Yeah, we can have this inspection. Even a very small fruit, like a very small or tiny orange juice, yeah, it's Tentang orange juice. We can see a very clear detail of inside of the if you compare with the when we cut the oranges, so it's very clear, and this is help us. Actually, we can apply this for another fruits. Yeah, actually, it's I think last year I went to Tsinghua University, and also some company now they create a very quick durian inspection. So you know durian is a very expensive. So they just in 10 seconds they after a very sophisticated algorithm and using AI, they can recognize internal and evaluate the quality of durian without distracting the durian. So this is the potential of non-destructive inspection of agricultural product. And also some of our research are also interesting to scan their research on the space rocket research. So we use scanning the tube and also the propellant. Yeah, so they try some recipe for how to make a very good propellant, and we can inspect the porosity inside of the rocket propellant, and also using the CT we can help them to inspect very clear in, like, I think it's 200 micron, yeah, internal of the composite materials. So this is helpful for us, yeah. And also this is the newest our research. We try more advancing CT using a dual energy CT, as I present in last year ICARS. The dual energy CT applied for the fossilized molar specimen. Actually, this is fossil is around 2 million years old, yeah, and we scan it using a 90 kilovolt and 150 kV X-ray spectra, and we use copper filtration, and we enable visualization in the internal structures and micro cracks, and this is support material differentiation of fossils and also preservation studies. So here is one specific for a fossil example. So you can see we scan it the same fossil in two different conditions, and then we reconstruct, and you can see the very detail of internal part of the fossil, yeah, including the crack, the intrusion of the materials among the teeth, and also the jaw bones. Yeah, so we also can using a software we can visualize the 3D dimension, and we can our researchers can make a further analysis from these very important fossils. So the specimen is a Serpidae molar fossils from the Pucangan Formation, Sangiran, and we use dual energy reconstruction to improve the interpretation of the fossilization process. So based on this research, we identified several directions for the future works. So this is development of new, this is still new, I think in the last 2 months, new dual energy fluoroscopic detector. So with a single exposure, we got dual energy CT using a dual layer scintillators, and we use advanced dual energy reconstruction algorithms, and also using this one we can doing a multi-element material calibration. So this is the our prototype of dual layer scintillator, as I told in last year ICARS to some of the fellow that's very interesting. So actually we open for the future collaboration, yeah, how to improve this prototype to can be applied for wide use of the radiography or CT system. Yeah. So you can see starting with the design, yeah, mechanical design. So we change from the stainless steel, aluminum, and then acrylic. Now we're using the acrylic. Yeah. Why we choose this one? Because it's easier to fabrication. We have laser cutting, and we can produce this one in less than 1 day, whole system. So first time we have to like design the camera box and also the shielding, especially to shield the camera. And recently we replaced the camera with a very new interesting technology of camera. We use astrography camera. So why we use astrography? This is a very good camera for low light, and we can expose for a long time. Yeah? So you can see when we observe the space, stars, we can open this camera for like around 10 minutes, even 20 minutes. So for the certain condition, we can still use this for different kind of situation of the fluoroscopic. So we also using Monte Carlo simulation to define that the shielding is effective enough, yeah, using artists, and then we implement this and fabricate using lead shielding and integrate with the whole camera, yeah. So and then we have optical calibration using a astrographic camera. It's very interesting. This camera have a internal cooling system, and this is very good because this is can be reduce the noise, yeah, and that's why we can expose this camera for longer time for actually for the certain case, yeah. So we also have a drawing design and fabricated the prototype, and we put this detector on our compartment, and we use the laser alignment system and try at the beginning of the first box, and then later we will combine these two fluoroscopic box for dual energy detectors. So we also continuous improvement for fluoroscopic detector NCT with the mechanical optimization and optical alignment, noise reduction, and using a dual scintillator sandwich design. And also in the future, we also, and currently we improve the flat field correction, bad pixel removal, real-time imaging processing, yeah, and also advanced reconstruction. It's like we also apply the reconstruction methods, yeah, with the iteration method, beam hardening correction, and using a dual energy, we can make a material discrimination. And this is a very interesting because some of our colleagues now it's more focused on AI and deep learning, and this is very very interesting because using AI we can reduce the time of the acquisition. We can create and predict the projection, so actually we can reduce the number of projection and better reconstruction, yeah. So mechanical, optical, software improvement continue to enhance the performance. So advanced reconstruction methods also applied, and also the AI and based techniques, and also everything is being explored. So this is important for, actually I'm not pure talking about the science, yeah, but this is more engineering, but this is very very interesting, and it can be applicable for any country, especially developing countries, since based on the IEA design, this design is very very easy to modify and adopting our needs, yeah. So we applied the scampers. So scampers is a innovation by asking simple but powerful questions like substitutes, yeah, and combine, adapt, modify, put the other use, eliminate, or reverse. So we can replace one part with the other better works part. Yeah, put the different components together to improve, update the product to new preferences, and change the appearance and presentation, and also use their product for purpose that wasn't intended. Yeah, it's like it's like astrographic camera is designed for the astronomy, but we can use this advancement for the radiography. Yeah, we can eliminate the useless part. Yeah, for example, from the beginning design of from the bump, it's very heavy. It's like more than 20 kilogram, but now we can reduce less than 10 kilograms. So, and also we can combine all the scampers method for innovation. Yeah. Finally, in conclusion, we have successfully developed and implemented a low-cost fluoroscopic detector and CT system based on the IAA guidance. So the system was demonstrated real industrial and non-industrial application. So contributing to technology accessibility and also capacity building. This work strongly aligned with the IAA mission, and using the collaboration center, we in the future open for the collaboration and also contribution for all the colleagues here to continuous improvement, and also not only improve for research but also try to deliver this to the real industry. So I think this is can help like not the sophisticated or high cost industry, but even for the low industry, we can help them to improve their product for safety and also for better economy. So thank you very much for your attention. So if you have any question, you can type on the chat or we can discuss later on the Q&A session. Thank you so much. I return to Mr. Rozik.
Thank you very much, Pak Chris, for your clear and informative presentation regarding your experiences on development of low-cost city. As we learned from your explanation that you started from the very simple one, only for the one part with using the fluoroscopy, and then step by step develop it, and now you finally can produce a complete system for the low-cost city, and now you are still conducting on continuous improvement. Now you mentioned on dual energy system. Okay, we now move to the second agenda on this today's webinars. So it's my pleasure to invite Hannah, industrial technologist from the IAEA, to present and launch the new coordinated research project. Hannah, the screen is yours now.
Yeah, thank you so much. I'm trying to share. But I don't know whether Chris is still sharing because I'm not able to share. If Chris can stop sharing. Can you hear me?
Yes.
Yes, I have stopped my sharing.
Oh, okay.
Yeah,
right.
Please start. Yeah, I will give you 15 minutes, Hannah. Yeah,
Okay.
please use your time. Yeah, you still have a lot.
Sorry, for Hannah, you have to give him 20 minutes.
Okay, yeah, I agree. Please, Hannah, 20 minutes for you.
Rosie, can you share the slide for me? Because for some reason, I don't know. Yeah.
Okay. Please. Yeah.
Perfect. Okay, thank you so much, ladies and gentlemen, joining us on this webinar. My name is Hannah. I don't know why my video is also not really working. I don't know whether you can see me because I can't see myself, but the video is on though. Yeah, so I'm grateful to the organizers of this webinar, that is BRIN, which is one of our important collaborating centers in the area of non-destructive testing, as well as radioactive traces and applications in industry. And thank you actually to also Malaysia and to Morocco, who are part of our IAA collaborating centers. I also want to thank Christijo for making time to take us through this presentation. So this afternoon, I'm happy and I'm glad for the opportunity given me to be part of this webinar series to share this new CRP on enhancing disaster management with AI augmented NDT for engineering assessments with you, so that you know what is happening at the agency and how to position yourself to apply and participate in the CRP. Next slide, please. So this will be the order of my presentation. Quickly, I'll provide some context for the CRP and then now focus on the CRP itself and how you can apply, and then I will conclude and acknowledge. Next slide. Yes, so as some of you may know, the IAEA's projects and programs are always based on research. So they are research and development based. And what this means is that before we go on to implement any projects for our member states, who are the main drivers of our programs, there has to be the research and development support to justify the transfer of this technology to member states. And so we do that through our IAEA laboratories, through our coordinated research projects, through our collaborating centers, which I talked about earlier, through technical meetings, and also through consultancy meetings. And so the R&D starts from this level, and then it goes on to advance CRPs if there is the need, or we go on to build pilot plan to sort of demonstrate what the technology can do. And once this is ripe, the technology is then transferred through TC programs. So the transfer can be done through TC projects, be it regional or national. We have fellowships, scientific visits, expert missions, and education and training. And this is how the agency's work runs. And through this, we're able to support about 9 out of the 17 SDG goals. Next slide, please. So to provide a brief account of the past and what has informed the CRP that I'll be sharing details about. So in the space of the past 10 years, I mean, the agency's member states have suffered a lot of disasters. So we can talk of Ecuador 2016, Mexico 2017, Albania 2019, and Lebanon in 2020. And in all these cases, our member states were hit by very devastating earthquakes, which we know don't only affect human lives, which is key, but also affects infrastructure. And when these disasters happen, member states obviously have reached out to agency for support. And in such cases, agency has also provided support to its member states through a number of activities. Next slide. And in the course of that engagement with member states who had been affected by disasters, there was a need to come up with an emergency response plan. So please note that this is different from the IEC, which is the Incident and Emergency Response Plan. That one deals with nuclear accidents and incidents. But as far as the NDT is concerned, we are talking about non-nuclear incidents. So you talk about earthquakes, you talk about tsunamis, you talk about hurricanes, for example, and that is where the NDT Service Center Emergency Response Plan kicks in. So we also deploy response to our member states through our collaborating centers. So for now, we have 3 collaborating centers who are involved in NDT. And then we also have an international pool of experts, I mean the International Committee for NDT, which is the global focal point for cooperation in NDT worldwide. And then we also have our IAEA regional designated centers. So these are the centers that we have built. These are the partnerships and collaborations we have built over the years, together with, of course, the local governmental agencies and non-governmental agencies, disaster management organizations, security services, and NDT centers global, through which we coordinate this NDT emergency response plan. Next slide. And so over the period, we have managed to build capability in NDT-CE. So you know that NDT is old, non-destructive testing application in industry is a very old application, very matured application. But in terms of NDT for civil engineering assessment, it is what we like to call an emerging area. And so over the period, through this kind of NDT response that we have provided to member states, we have built capacity in about 20 member states with the support of some of our member states who are already resourced or who are already advanced in this particular application. And together with them, we have built a certain level of capacity in non-destructive testing and its application in civil engineering and how it can be used to support disaster recovery outcomes. Next slide. Now, we realize that it would be important for the agency to adopt a more proactive approach rather than a reactive approach when disaster happens. And so in that spirit, the agency established a non-destructive testing center lab in Cyprus, which was opened just about the tail end of 2024 by the Director General, actually supported by the government of Japan as a way of contributing to the agency to support its member states who are hit by disasters. And so we have this lab in Cyprus, which is equipped with state-of-the-art equipment, as you see on your screen. And then through this center, we are able to provide training to our member states in this area of application in advance so that in the likely or unlikely event of a disaster, these member states will be equipped to be able to apply these technologies for their own benefit. Alongside the establishment of the lab, the agency has also developed guidelines on training. As I mentioned earlier, this is an emerging field, and so there is a need to come up with a training syllabus that will be able to assist the training of our member states in this very important area. And so over the period, over 200 persons in our member states have been trained. Now, in addition to these guidelines on training syllabi that has been also issued, we are also in the process of launching an e-learning training program solely focused on this NDT for civil engineering. And at the same time, we have our international partners in the ICNDT Specialist Working Group on Standards, pushing very hard to ensure that we develop global standards through the ISO to be able to qualify and certify personnel who decide to receive training and apply NDT for civil engineering applications. Next slide, please. Yeah, so now to our new CRP, that is CRP whose story was just published yesterday, that is under the code F22087, entitled Enhancing Disaster Management with AI Augmented NDT for Engineering Assessment. So, and the slides I shared earlier gives you actually a picture of where the agency has come from and where we want to go from now. Next slide. In addition to the previous catastrophes that happened over the period, we know that in recent times, Morocco, Turkey, Syria, and Myanmar, and even in recently, Jamaica, has also experienced several disasters. And these disasters seem to be increasing in their frequency. And again, not only human lives are lost, but also there's damage to infrastructure, there's disruption of lifelines, in terms of water, energy, transport, communication, and so on and so forth. And we realize that post-disaster of assessment of the damage of civil structures is always very important to determine the safety and functionality or otherwise of these structures that are affected. And that is where the value of NDT comes in, because the NDT is used to now detect hidden damage, which sometimes otherwise are not visible to the eye. And so then you have NDT coming in to provide added value and to be able to help assess the extent of damage to these civil structures after a disaster has occurred. And over the period, agencies' contributions has been through expert missions to the sites itself and through capacity building. And as I mentioned, the recently launched non-destructive testing center. Next slide, please. Next slide, please. Yeah. So the whole idea was that agency has been supporting member states with this emerging field of NDT application for the past 10 years. We have gathered some experience, but also looking at the trends, we know that AI is the future. And we see the potential value that artificial intelligence can add to the conventional or traditional NDT that we have. And so we came up with this CRP that has the objective to strengthen disaster resilience by developing and applying AI-enhanced NDT methods that enable rapid, accurate, and practical structural integrity assessments for effective disaster management. Next slide, please. And so specific objectives will be, first of all, to investigate AI and other emerging technologies for developing advanced NDT methodologies applicable to complex disaster situations. So the point is that the NDT methods, as we know them for civil engineering, are great. We use them on the field, but through this research, we want to really establish which one of them is very appropriate for complex disaster situations, because not all of them might probably be very useful in such scenarios. And then we want to go on to design experimental studies to generate data sets for training and validating AI models used in NDT for civil engineering. Data is always at the basis of AI applications, and a lot of data, the more data you have, the better you have. But again, what is the format of this data? Data formatting is a very key part. And so this CRP will seek to design experimental studies that will help us to collect the appropriate data, which will then be used to train the AI models that will be used for NDT in civil engineering. Then the CRP also seeks to establish protocols and data standards, yes, for the collection, for the processing and sharing of AI-enhanced NDT data to support interoperability and coordinated disaster management. Then again, the CRP will develop and validate the AI-augmented NDT methods that improve the speed, accuracy, and reliability for post-disaster structural assessments. And then finally, to create a framework for effective integration of the AI-enhanced NDT methods into engineering assessment, because we realize that on our missions with our experts, even the civil engineering community or the structural engineers don't know what NDT is about. And so they have their own protocols based on which they determine the safety and functionality of these structures. But we feel that NDT has a potential to add some value to what they do. So at the end of the CRP, we are looking to be able to integrate the AI enhanced methods into existing engineering assessment frameworks in our member states. Next slide, please. So NDT methods, which we usually employ, are quite a lot, but then we also we are open to other NDT methods which are applicable to non-destructive testing in civil engineering. Popular ones which we work with are the rebound hammer testing, ultrasound pulse velocity, impact echo, tomography, rebar testing and detection, gamma radiography, and computed tomography. And so at the end of the day, we hope to present to our member states a comprehensive suite of solutions for the benefit of our member states for strengthening their disaster resilience. Next slide, please. So once the CRP is done, expected outcomes will be that we would have strengthened disaster resilience by the application of AI-enhanced NDT methods for rapid, accurate, practical, structural integrity assessments for effective disaster management. And then would have developed and trained AI models, would have benchmarked these AI models and their NDT for CE methodologies. And then we would also have integrated AI-enhanced NDT outputs into engineering workflows, and we would also have protocols and guidelines for enhanced AI NDT applications in civil engineering. Next slide, please. Yeah, so if I would probably share the story or my colleague, if Shangwan is on the call, Shangwan, you can share the story and the link to the story in our, yes, I think he's just shared it now. So this call was released just yesterday. And you can visit the link that my brother has shared so that you can have more information about the CRP. But actually, the deadline, we are expecting a maximum of 15 proposals, and this is very competitive. We also encourage the participation of women in the project teams that are going to work on the CRP as much as possible. And the deadline for submission of proposals is just about 1 month from now, that is 27th of February, 2026, because the first research coordination meeting is planned for Q4 of 2026. I would want to also comment on how to participate. There's yet another link on how to participate. Shangwan, you can also put that one in the chat. But if you can also click on that one, maybe if the one, yes, can click on that in the link, I will maybe say a few comments about the proposal. If you can click on that link, it could take us there. Or it's not working.
Yeah, it's because it will go to the another page, so
Okay.
yeah.
But that is fine. We can go to another page because I just want to point something out there on how to participate.
Okay. Okay, so I will stop share first.
Okay.
And then this one.
Exactly. So if you go down there, please go down, and then you click on the proposal. On the right side there is research. Yes, proposal for research contracts and agreements. You can click on that.
Oh, this is downloadable.
Okay. Well,
the
but I want to
proposal.
encourage attendees to visit the website. Here, you have detailed information on how to apply either via a research contract or a research agreement. Developed countries apply through research agreements, and developing countries apply through the research contract. And there are some little differences to research contracts and agreements. If you have a research agreement with the agency on a CRP, you do not get the annual contract payments. But if you have an agreement, you have a contract, I beg your pardon, then you have this annual payments of contracts after you submit your report. And so please visit this website. And then if you have any questions, you can write to me and I will be glad to answer them. Thanks. So we can go back to the slide. Yes. Next slide, please. Yes, so that actually brings me to the end of the presentation. But at this point, I want to really I want to appreciate our international experts who have supported everything that we have done. They're actually a big part of what we do. They helped us to develop this proposal actually through a series of technical and consultancy meetings. And then they also supported our NDT emergency response missions and are now developing protocols to be able to use NDT in disaster situations. And they have also developed the training guidelines on NDT, which I talked about earlier, which we are using currently in our trainings. And then are also helping to develop global standards for NDT personnel qualification and certification. And I want to say that we are very grateful. And these documents, actually, as we have them, are very important documentation for the CRP, and the CRP participants will get to benefit from it and on how they can better conduct the research. And so thank you. Next slide. Thank you very much for your attention. And I think that I can take some questions from here. Thank you.
Okay, thank you, Hannah, for your explanation regarding to the new CRP. And now we can proceed to the Q&A session. Yeah. And so let me check to the column chat first, whether is there any question or not. So there is one question. Yeah. Thank you for a nice presentation. I wanted to ask what is the major contributing factor that made it possible to reduce the cost of this X-ray CT machine as compared to the other existing X-ray CT machine? This is, I think, the question for Pak Chris. Yeah, please answer the
Okay,
question.
thank you very much, Witness Sirumi, for your very interesting question. Yeah. So actually, as I mentioned on my presentation, actually this project is like a DIY project. Yeah, since we improve and we create the most important part of the CT system, which one is detector. So when we have a CT system, the detector is also a very expensive part, yeah, and also the X-ray, yeah. So you can see why there is very different difference of the cost of this system, since one is we develop the detector itself. So the detector is very significant cost of the system. The second one, for the compartment, the design, we design ourselves, and also the software for the acquisition. So this is save a lot of money, yeah. And also we also introduced a lot of open source software, yeah. So as I mentioned on my presentation, this is not only using the property right software. Actually, currently there's a lot of open source software for reconstruction, for visualization, yeah. And also probably the difference is like I know this is the not good part for our design is the X-ray. We use the just 0.4 focal point focal spot X-ray, but on the commercial usually they use the mini focus or micro focus. So actually that's why they will have a very clearer image and also better resolution. But based on our comparison, actually we did some comparison with the same object, and we put on our CT system and also put on the commercial system, and the result is not so different. So I think depend on if you concern with the nano CT or micro CT with like less than 100 microns, so we cannot use it. But at least this system is based on our experience, it's affordable and it can be applied for various application, yeah. And I think this is still open. You can customize the system depend on your need or purpose. Yeah. Okay, I think that's my answer for this question.
Okay, thank you, Pak Chris, for your explanation or answer regarding to the question asked by witness. Yeah. So there is one question also from Pak Nazrul. Can the design CT scan also be used in the health sector? Have you implemented CT scans in the healthcare sector? Yeah, so please answer this one.
Okay, thank you. This is a difficult question, yeah, since actually we more focus on the industrial and city, because when we try to move to the medical, actually there's a lot of things that we have to improve, yeah, especially for the Actually, my colleague from another university also tried to use this fluoroscopic for the medical, but it's still underdeveloped, yeah, and it is take longer development, since for the health there's a lot of requirement, safety requirement, and also more complicated mechanical and also reliability. So I think currently we just still focus on the non-medical application, yeah. But probably in the future, yes, we can.
Okay, thank you, Pak Chris. And the next question is for Hannah. Please answer this question, Hannah. The first one is, what is the role of AI and entity system for disaster management? And the second one is, what data is required for AI to be used in the system?
Okay, thank you very much, Nazru, for the question. So we know what artificial intelligence is capable of doing these days. And the fact that they can, for example, if you take the imaging systems, AI can actually help us reduce the number of, for example, projections that we need to do. And it can also enhance our data analysis and treatment, even enhance the data, the data processing and image acquisition. So we know that AI can do a lot for example, for tomography, even for radiography. And then if you take even, for example, rebound hammer for concrete strength testing, depending on if you are able to gather a minimum amount of data and train an AI model with it, it is possible that you don't have to in future take more samples over a test space to be able to determine the strength that you're looking for. So actually the role of artificial intelligence in NDT testings is quite great. And we feel that if we're able to harness this, first of all, in our response to disasters, we can be timely. We can also improve on our accuracy of the interpretation that we give. And that is what the project is about. And then if you talk about the data required, it depends, because every NDT method has a different output. If you take, for example, the rebound hammer, the output you get just numerical figures. These are single data that you have. But if you also take an NDT method, like, for example, tomography or radiography, you have an image. So depending on the particular NDT method you are using, the data required is different. And as part of the CRP, we want to try and see how we can harmonize the collection and format the NDT data outputs and present them in a way that our AI models can use. So I hope that that answers your question.
Okay, thank you, Hannah. Just for your information, Professor Nazrul is my counterpart on our research, yeah, mainly and the AI. So so that's why he is interested in your CRP now.
Perfect.
And
thank you.
now
Thank you, Prof.
we are okay. Now we are going to the next question. Is there any focal spot size limitation of X-ray source for CT, Mr. Chris?
Okay, sure, Sanjoy D, yeah. So focal spot is very important parameter for the CT. So for example, in our CT system, we just use just a standard, not so small focal spot. So it's just 0.4 millimeter focal spot. So that's why I cannot make a magnification. Yeah, it's close to the parallel usually. So that's why when we have a micro focus or nano focus X-ray, probably we can improve our system, yeah, and we can make a magnification. So that's why if I can share my presentation, hang on a second. Yeah, you can see actually in our okay. So this is we experienced this on the when we yeah, you can see this. We used a big focal spot, and to improve this one, we have to put the object far from the source. Yeah, but if we can have and we replace this X-ray source with the micro focus X-ray or nano focus X-ray, we can move the object closer to the source, and we can have magnification. So that is the differential of the micro focus, and in this actually is close to the parallel beam. Yeah, but this is still enough because we have a very good camera. So it's like 20 megapixel camera. It's very very good. Yeah, so that's why sometimes we don't need for the magnification, but in the future, if we need more inspection for the for example, insects or nano material inspection, we need for the magnification. So we have to replace the focal spot of the X-ray using the better one, and we can got the clearer image, and also we can make a magnification. So the image will be much bigger and higher resolution. So that's why if we compare with the like this one, SkyScan, they have a I think, yeah, it's very because they use very have a nano focus, yeah, nano focus X-ray, and this is also expensive, yeah. And if we replace the system with the nano focus X-ray, I think this will be improved and same, because the difference is only on the detector. We develop ourselves detector and create whole system ourselves. Yeah, that's all. Hopefully this is can help you understand.
Okay, thank you, Pak Chris, for your answer. And the last one is Witness Sirumi asks you, Pak Chris, to share your email address, yeah, to him. Please use the private message to him or to her, yeah.
I put on the chat.
Okay, okay, thank you.
Anybody will can email me. I'm open with the collaboration and discussion.
Yeah. Okay, thank you very much, Pak Chris. I do believe that among you still have questions, but unfortunately, we already have reached to the end of this webinar. Now, so I would like to thank again to our speaker, Pak Chris and Hannah, for their valuable contribution. So thank you to all participants for joining us and for your active participation. This concludes the scientific presentation session. I now return the screen to our host, Ms. Damar, for the closing remarks. Thank you and have a pleasant day.
Thank you very much, Mr. Razik. Okay. Dear all participants, we are at the end of our sessions. Let us hear the closing remarks by the head of the Research Center for Radiation Process Technology, BRIN. Please welcome Mr. Irawan Sugoro. You are still muted, sir.
Okay.
Good.
Okay now.
Yes.
Hello.
Yes, we can hear you, sir.
Okay, sorry. Good evening, good afternoon, good morning. Assalamualaikum warahmatullahi wabarakatuh. It's an opportunity to outstanding speaker and all enthusiastic participants for the IAI Collaborating Center webinar series, Advancing Industrial Radiation Technology. This webinar has provided us with a wealth of knowledge opportunity. We hope the knowledge shared today is beneficial and become a catalyst for all us, cause for research and innovation, also for industry, and open opportunity for next collaboration. Our thanks again for the speaker, Mr. Kristejo and Ms. Hannah, for introducing CRT program related activity. IAEA, BRIN, and the webinar committee. So see you at the next event. Wassalamualaikum warahmatullahi wabarakatuh. Good evening.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Pak Irawan. To all participants of this webinar series, I apologize for the mistakes we made. We appreciate your attention and active participation. See you on the next IAEA webinar series. Good day. Wassalamualaikum.
Waalaikumsalam.
Thank you.
See you.
Waalaikumsalam.
Thank you, Hannah. Thank you, Selina. Thank you, Liu, and also Geraldo.
Thank you.
Are you there? Are you there, Geraldo?
Thank you, everyone.
Thank you, Chris. Thank you, Hannah. Bye-bye.
Thank you too.
Okay.
Bye. Bye-bye all.
Thank you,
Bye
Hannah. Thank you, Chris.
all. Thank you for your participation.
Gracias.
Terima kasih Bu Arti dan juga Bu Damar, juga Mbak Martini dan juga yang lainnya, nggih. Tidak bisa saya sebutkan satu persatu. Terima kasih atas supportingnya untuk kesuksesan hari ini. Terima kasih Bu Ros atas
Terima kasih Pak Dimas, supportingnya
partisipasinya.
juga.
Ya, Pak Dimas juga.
Bye, Rosi. See you.
Bye, thank you.
Bye.
Pak Rozi, Pak Chris,
Iya,
semuanya.
oke, Habib, yes. Okay, Abdul Aziz, you still there?
More than almost 100, yeah, I think.
Yeah, around 100, yeah, because we have also streaming use YouTube.
YouTube, yeah.
Yeah, YouTube, yeah, there is more than 10 people watching via YouTube, yeah. Oke ya, Pak Tris, terima kasih. Saya izin pamit ya, Mbak Damar, Mbak Martini, Bu Arti.
Thank you.
Saya mohon pamit.
Damar.
Terima kasih sekali lagi atas supportnya semuanya, ya atas terselenggaranya webinar pada malam hari ini. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh.